Okay, so we're still sticking with systems of differential equations, obviously. This is yet another option that we have, is to introduce the Laplace transform method, which is actually not going to be all that different than what you're used to doing. When was it a convenient thing to do, to use Laplace transforms? Never. We hate Laplace transforms, right? When was it really nice to use Laplace transforms? When you... Yes? Yes? What else? What's that? Yes? Initial conditions, that's what we're talking about. That's what I'm looking for, right? So all of what Aaron said, and if we have initial conditions, as Danny specified, good option. So when we have initial conditions for these systems, using Laplace transforms, reduces the systems to basically just algebra. So I'm basically going to go through one example, and then I'm just going to have you guys try a couple. Pretty easy section today. Let's say we have 2x prime plus y prime minus y equals t. X prime plus y prime equals t squared. And the conditions are that x of 0 is 1 and y of 0 is 0. Okay. When we were doing Laplace transforms last unit, I think our first step was just to take the Laplace transform of the entire thing and plug everything in, right? So let's do that. So if we take the Laplace transform of x prime, so we're taking the Laplace transform of everything, we get, let's see, 2, and then it was x, s times x of s, minus x of 0, plus, now we take the Laplace transform of y prime, so that's going to be s y of s minus y of 0. And then the Laplace transform of regular y is just capital Y of s. The Laplace transform of t is 1 over s squared. And we do the same thing with the second equation. We get s x of s minus x of 0 plus s y of s minus y of 0, and that equals the transform of t squared, so that's 2 factorial over s cubed. Alright, so I'm going to group all my x's together. So from the first equation, I just have 2s plus, and now I'll group y of s together. So I'm going to have s minus 1, and I'll get everything else on the other side. Y of 0 is going to cancel, because that's equal to 0. X of 0 is 1, so that's actually minus 2, so when I move it over, it becomes 2 plus 1 over s squared. Okay, and I'll do pretty much the same thing with the second equation. We get s capital X of s plus s capital Y of s. Move the initial condition over, we get 1 plus 2 over s cubed. So this is equal to 1, and that's how we get these two. Okay. Well, looks like I could easily cancel out capital X. So maybe what I'll do is double bottom equation and subtract everything. So then the x of s's cancel, and then I'll get s minus 1 minus 2s y of s and then we just get 1 over s squared. 2 minus 2 is going to cancel here. And then 1 minus 4 is... Oh, we can't combine those, so... We could later if we wanted to, but for now we have 1 over s squared minus 4 over s cubed. Okay. So this becomes minus s minus 1 Actually, let's put these together. So this will be s cubed, and this will be s on top. So we have s minus 4 over s cubed. Get rid of the coefficient of y. I'll put the negative or distribute the negative to the numerator, so we get 4 minus s, and now this becomes s cubed and then s plus 1. And now you could either try convolution theorem. I'm not sure why you would do that, however. I would just do partial fractions here. Decomposition would be what? A over plus. Good? Yep. Alright, clear the denominators. So we get 4 minus s equals as squared times s plus 1 plus bs s plus 1 plus c s plus 1 and plus ds cubed. So I'll start with the cubes. We have as cubed plus ds cubed, so a plus d has to equal 0 since we don't have any cubes on the left. The square terms, we're going to have a plus b, and again that equals 0. The linear terms, we have b plus c, and that has to equal negative 1. And the only constant we have is c, so that equals 4. If c is 4, then b has to be minus 5. If b is minus 5, then a has to be 5. And if a is 5, this is a nice one, d has to be minus 5. So we get that y of s, if I plug all these back in, has to be 5 over s minus 5 over s squared plus 4 over s cubed minus 5 over s plus 1. And from here, once you have a good idea of what y of s is and you have it in a nice convenient form, now you apply the inverse transform to the whole equation. We get y of t is equal to, let's see, so what's y inverse of 5 over s? It's 5. This would just be 5t. We want that to be 2, so this would be 2t squared minus 5 translated, so e to the minus t. Okay, so there's y of t. Bless you. And now we have a decision to make. I'm going to go with okay. So once I have one of these solutions, if you go back to where you took the Laplace transform of everything, you could plug y of t back into one of these equations. Or not y of t, you could do y of s, sorry, since we know what y of s looks like right here. That's what I meant to say. So we're going to use this one here. In one of these, and I think the second equation is probably a little easier to work with. So since I know that s times x of s minus 1, that's the initial condition for x of 0, plus s times y of s equals 2 over s cubed. What I'm going to do here is isolate x of s and plug in what I know and then go from there. So if I get x of s alone, I'm going to divide by s, so 1 over s plus 2 over s to the 4, and then we're going to have minus y of s. So after you divide by s and then get x of s alone, you get 1 over s plus 2 over s to the 4 minus y of s. And see, now once you have the first one, it's not too bad. So here we apply the inverse transform again. So now we got x of t. X of t, inverse of 1 over s, is just 1. The inverse of 2 over s to the 4, that comes from cubed, so 1 t cubed, and it'd be 1/3, because it's 2 times 1/6, which I'll clean up later. Minus, and now what we want to do is plug in y of s, so I still have yet to take the inverse transform of, whoops, wrong box. Darn it. Ignore that arrow. What I want to do is plug this in here and take the inverse transform, which I have the answer to. It's this one right here. So x of t will be 1 plus 1/3 t cubed minus the quantity of, and now when I take the inverse transform of y of s, I get exactly y of t. So that's 5 minus 5t plus 2t squared minus 5e to the minus t. And if you distribute and simplify as much as you can, you get negative 4 plus 5t minus 2t squared plus 1/3 t cubed plus 5e to the minus t. Okay? So that's the basic idea of systems with Laplace transforms. We'll just do a couple of applications now, and you guys can work through those, but I'll help you set them up. Any questions on the idea here? So just Laplace everything, plug in your conditions, get either x or y alone, find out what x of t or y of t is, and then you can go back, plug it into one of the equations to figure out the other one. So it's not quite elimination twice. You can just do it that way. Okay. All right.